lectures, but it's not very hard. Also, you can find this in... Это? Я ее никогда не использую. Okay, so I'm leaving this as an exercise. And so this says proof is exercise. And the next proposition, which in some sense is analog of the proposition that I proved on the previous lecture, and actually involves more or less the same ideas, but at some steps, of course, the technical work is a little bit different. So I'm going to say that a simplicial set X is isomorphic to the nerve of a category if and only if, so that's another criterion for a simplicial set to be a nerve in terms now of these spines. If and only if X has unique extension along inclusion of the spine into the n-dimensional simplex, where n is at least 2. Remember that this condition just simply means you start with a simplicial set, you have, well, it is given to you a map from In to the x, so this is included into the delta n, and there is kind of unique extension to the whole simplex. Okay, so that's going to give you another way to characterize the image of the nerve functor. Instead of the horns, you're using now the spines. And when we want to generalize the notion of a category, right, we kind of want to, well, consider something like a simplicial set, but we want to drop some conditions. Like, for example, if we use what we've done on the previous lecture with the unique extensions along the horns, we can drop the uniqueness. What you get as the result is called quasi-category. So here, you can also drop something, and this is the reason why I'm formulating this proposition, which is, again, proof is left as an exercise, since this is more or less the same of what we've done before. So here, this uniqueness you can formulate as follows. You have a map, which is, I'm going to call phi n, and this will be from the xn to this home from the spine to the x, which I'm going to write like this, right? And the previous proposition tells us that this map yn is actually an isomorphism. So that's the way to characterize a category inside simplicial sets. But we can kind of generalize this, right? And so, for example, we can take X to be not a simplicial set, but simplicial space. To be a simplicial space, which is actually quite often understood as a bisimplicial set. And so simplicial set and the category of simplicial sets. So you can also try to do this with the simplicial objects in the category of topological spaces, but technically it's more convenient to work with bisimplicial sets. But so anyway, we're not going to go into any details in this theorem, just want to indicate what other directions are possible other than quasi-categories. So when you have this simplicial space, you still get these maps, right? So we can require that phi n, so if we assume that the same maps as before, phi n, are weak homotopy covariances, so then such X is called Siegel category. Well, so you can kind of think as a generalization of an ordinary category to be the Siegel category. Well, you just kind of take this to be a simplicial space. You instead of being just an isomorphism of sets, you get some weak equivalence of simplicial sets in each position. But it doesn't work nicely. you still, well, kind of, if you want to think about this, remember when we constructed categories, x0 was always something like a set of objects, a class of objects, right? Now in this case, if you just take this single category, x0 is a simplicial set, or topological space in other versions. So it's not very nice. So you need to add this kind of a single category, some other technical conditions. For example, you can just require that x0 is a discrete topological space. Or there are other requirements. And so kind of using this condition with maps phi n and weak equivalences, there are two directions. I think they call something like, you can require completeness for the x0, and this is called complete single spaces, or you can require discreteness and you get this single categories. And there are other technical conditions. So it is possible to kind of start with spines and come up with some theory generalizing categories using this single stuff. But we're going to go in the other direction, so this is why I'm not going to give you any details. And you can read about this in the Bergner's book on homotopy theory and infinity one categories. It's sure.
What is the relation of sets by n to x? It's not in space or something else?
What do you mean here? Here?
In category as set.
No, this is home. Yes. So this home, well, this is just some set. You can compute this as a set like this. So this is just an isomer.
Can I ask a question about the middle word?
Uh-huh.
Phi n, what is it? It's just, first we introduced phi n, xn isomorphic to this.
Well, you still have this map, all right? You always have in is included to the delta n.
Yeah.
So it's on the homes, it induces a map.
Yes.
So this is the induced map. Well, and still, since this is not a set, right? So these are sets, and this will be not a set but simply show space. This is kind of, you also need to say something that you consider this as the discrete simply show space, and this also as a discrete simply show space. So you can embed simply show sets into simply show spaces. Yeah, but I just wanted to mention that there's kind of a completely different approach that give you different theories, but homotopically they are all equivalent, right? So on all, you can take quasi-categories, you can take one of the versions of the single categories. There are model structures on these things, there are homotopic categories, and the homotopic categories are equivalent. So homotopically speaking, these theories are equivalent, but kind of mathematically, there might be reasons why you want to distinguish them, but kind of if you also use some common sense, why quasi-categories is much better, because Lurie wrote his text on quasi-categories, and there's kind of complete reference for essentially all the facts about quasi-categories. And for single categories, there are no such nice sources. There are only original papers and some other papers, but there are no books, there are no sites, etc. Yeah, and another proposition that I want to mention, and in this proposition finish this first chapter, is that a category, say C, is a groupoid. Groupoid if and only if its nerve NC is a Kahn complex. Now this really doesn't require any new ideas. You just more or less take the previous proof that we've done on the previous lecture and just repeat this proof, assuming that additionally that this is a groupoid. So quite simple. So with this I want to finish the first chapter and now start the second chapter. So I will call this chapter 2 model categories, but really this will be just some elements of the model categories that I need for this course. Well, it's not possible to discuss everything about model categories in 2 or 3 lectures. So let me just emphasize stuff that I need to develop the theory. Okay, and first section, lifting properties. We already have seen lifting properties before when we discussed Kahn fibrations and Kahn complexes. Now I'm going to formulate abstractly some of the definitions and properties. So we can consider 2 morphisms. Yeah, let me also state in the beginning of the section that categories in this section has all small colimits. So we can take two maps, say let me write F and G in more C, just two morphisms in this category, and we can look at the following lifting problem. Right, just repeating what I've done before. So since the objects won't be important, only maps are important, I'm not going to give them names. So for two morphisms and two other morphisms such that this square is commutative, so this is the lifting problem. And the lifting is just the map that exists in this square so that the two triangles are commutative. So in this case, so we can say that G has right lifting property with respect to F, and dually I can say that F has left lifting property with respect to G. Just the standard terminology. So we have lifting problem, we have solution of lifting problem. In this case, we have this terminology for F and for G. And moreover, we have some notation. So to avoid writing this all the time, there is kind of a short and nice notation which will be used all the time. So notation, if you have a lifting problem and there is a solution of this lifting problem, I'm going to write this symbol.
So for any pair of horizontal morphisms,
Yeah.
we have a structure.
So for we have a lifting, so let's formulate it here. So G has a right lifting property with respect to F. This means that for any U and V, which is like on this picture, right, such that we have a composition of the GU is equal to the composition of the V and F, right? So there is, say, sigma, right? So this is map sigma, such that, well, don't want to write it, but these two triangles are commutative. So we have G has right lifting property. For any two maps U and F, you can find this sigma. U and V. Right. And I'm going to write this notation. So if the lifting exists. So you can think about this symbol as something like a predicate, right? So it is true, or the answer is yes, if there is a lifting for this F and G and for any U and V. So this is one notation, maybe first part. So the second part, you can consider two classes of morphisms. So let's say A and B. These are inside more C. And then you can write A, the symbol of the lifting, in the middle B. So this is just means that we have a solution of the lifting problem. So we have, say, A lifting with B for any A which is in the class A and any B which is in the class large B. So if I write this symbol, it means that somehow I want to show, or maybe I already know this, that there is this lifting for any pair of morphisms, one from A, one from B. And another notation is for the complements, so 3. I can take a class, so A is continue to be a class of morphisms in C, and then there is, say, right complement. So right complement is all the, well, maps G in the morphisms C, such that A lifting G exists. So there is a lifting for any A in the A. So this is the right complement, and there is also the notion of the left complement, which is of course defined dually. So these are complements with respect to the lifting problems. So there are trivial properties of the complements and there are less trivial properties. So trivial, I'm going to leave as an exercise. So lemma, which will be an exercise. So suppose I have two classes of morphisms and A is contained in the B. So then we have four very simple observations. So for example, if you take the right complement of B, this is contained in the right complement of A. So second trivial observation, if you take the left complement of B, it is contained in the left complement of A. So a little bit less trivial, but still very simple observation is that if you write right complement of the A, well, you can write this as follows. You take A, take the right complement, then to the result you apply the left complement, and then again right complement. And 4, which is a variation of the previous one, but for the left complement. So all these properties are more or less tautologically follows from just general categorical even set theoretical considerations.
Sorry, why do not we use the same observation of orthogonal classes?
Ordinal classes?
Orthogonal class, but it's not orthogonal. It's lifted property.
Yeah.
This class morphism of morphisms in your books name orthogonal morphisms.
Well, they're just another terminology, right? So you can instead of saying that this is complement, you can say this is left to right orthogonal. But this is just terminological remark. But there are also the notion of orthogonal with respect to the home. You can consider, for example, object and all the objects which are orthogonal with respect to the home and consider them a full set category. And then you can confuse two notions. And so for this reason, I prefer notation complement, not orthogonal. Okay. So I want to show that actually this, for example, the class which is the left complement, it's closed under a bunch of operations in the category theory. And before statement and proving this theorem, I just want to remind you maybe some terminology. So say a class of morphisms S is closed under push-outs if you have the following. So we consider a push-out square and say this is F, so this is push-out, this is F prime. So if F is in the S, this implies that F prime is in the S. So quite natural definition, closed under push-outs. So then the next thing is that this is closed under retracts, so definition. So let me, I want to avoid writing a class of maps S, so I'm going to just, in the following definitions, just write S. So S is closed under retracts. Well, this is like a standard closure under retracts for objects, but now for maps, meaning that we have a diagram of this kind. Right, and these two compositions are identities. So in this case, we can say that the map F prime is a retract of F. So F prime is the retract of F. And of course, closure under retraction simply means that if F is in the S, then the F prime is in the S. Okay, so maybe I can squeeze in the next definition also here. So S closed under coproducts Well, if you have the following, you have, say, a set Fi from the xi to the yi, So this is a subset inside the class S. So then the coproduct of Fi from the coproduct of the Xi to the coproduct of the Yi is in S. And the last definition says that S is closed under transfiniting compositions. So S is closed under transfinite compositions if for any ordinal lambda and any functor from the lambda to the category C, such that we have two properties. So first of all, x, I'll say I to the x I plus 1. So this is in S. This is one requirement, and another requirement is that if you take colimit over all the j less than I of xj, then the canonical map to the xi is an isomorphism. Okay, so it's closed down transfinite compositions is for any ordinal with this property. Of course, the most important one is this, that if you go from ordinal to the next ordinal, this is a map in the S. The map, which is the transfinite composition from the x0 to the colimit of x over lambda, is in S. Okay, so still next definition, a class of maps is weakly saturated, and I think quite often I forget to say this is weakly and call this just saturated. Weakly saturated if it is closed under three of these operations: push-outs, retracts, and transfinite compositions. So, and also you can say again, let's separate this definition into two parts. So if S,
So you mean we will call it saturated or weakly saturated?
well, I think technically this is called weakly saturated because you can also introduce the notion of saturated, which is stronger. But in this course, there will be no saturated classes. So all our classes will be only weakly saturated. So for this reason, later I might call this just saturated. I don't remember actually what's just saturated. I don't remember. So it's some different notion from the model category theory. Okay, so I want to say that if you have any class of maps, so if S is a class of maps, so then I'm also going to write S bar to be, so is the smallest weakly saturated class containing S. So there's this operation of weak saturation of any class of morphisms. Okay, so probably you might have a question why I define this closed under coproducts if this is not a part of the definition. Because for this property being closed under coproducts, I have a lemma, which is a straightforward exercise in category theory and manipulations with colimits. So another exercise. And this lemma says that, so lemma, so a class of maps S. So maybe if, let me say, if a class of maps is closed under transfinite compositions and push-outs, then it is closed under coproducts.
When we say class of morphisms, we mean that S is some class that closed under compositions.
It is, well, it is closed under compositions because it's closed for transfinite compositions, for example.
No, not saturated, just a class of morphisms, what we mean by it.
Well, it means that this is a subclass of all the morphisms.
Yeah, but it's just some subclass.
Just,
No,
well, yeah, well,
restriction.
no, there are no restrictions. But it always will be, of course, closed under compositions, because if you assume that this is saturated, usually for us interesting will be saturated, they're of course closed under compositions. But a priori you don't require anything. So for example here, when you take a closure, you don't a priori require that it's already closed under, say, finite compositions. Yeah, so proof is exercise, simple exercise in category theory. And this is just a kind of useful remark when you do some computations. Sometimes it's useful to know that whenever you have a, say, for example, weakly saturated class, it's automatically closed under coproducts. You don't need to prove this every time when you do a computation in some specific case. Okay, so how this is relevant to the lifting problems? Now we have the next proposition. So for any class S, the left complement is weakly saturated. Okay. So we just need to kind of separate this proof into 3 steps and check this is closed under push-outs, retracts, and more interestingly under transfinite compositions. So let's, as a step 1, consider push-outs. Push-outs. Well, maybe I use another blackboard. For push-outs, this is really simple. You kind of just draw one diagram, draw another diagram, and look at them together. Right, so for example, you have a push-out. Say this is F, this is F prime. And also, I want to prove the lifting property for the F prime, so let me draw this lifting diagram. So this is some map G. Right. So maybe I just write this in words to be more understandable. So lifting for the right square exists if exists lifting for the rectangle. Right? So if you can combine them together and look at this rectangle, if you have a lifting like this, then automatically get a lifting like this. So do you see why? Well, because this is push out. And you can just use universal property of the push out. right? So I need to construct a map from this thing to this thing. So here I already have a map. Here I kind of given a map, and that everything commutes. So this is, since I have a push out. Yeah, but lifting for the rectangle clearly exists, right? Because this rectangle is commutative, right? And by construction, this G is in the set S, and F was in the left complement to the S. So that's the case of the push-outs. So now let's consider the case of the retracts. Again, just look at the two diagrams together. So one diagram is saying that you have a retract F prime of the F. And the second diagram is saying to us that for F and for some G, again G is in the S as before, so we have a solution of the lifting problem. Right, but then, well, you can kind of look again at these things together. So look at the big diagram. This is G, F prime, and F. Right, so you want to construct the lifting. Now, this is where you want to have a lifting, right, for the F prime. Right, but then you know that if you look at this rectangle, so on the right, you have a solution for the lifting problem, which is given to us. Right, and then, well, if you want to, well, you have this solution of the lifting problem, you want this to get this solution, you can as well just get this solution, right, from this vertex to here. But you can just take this composition of this and this. Yeah, so I'm saying that if I'm trying to solve this lifting problem for this small square, right? Well, I can as well, since these two compositions is just identities, since this is a retract, right? I can as well just solve the lifting problem from this vertex to this vertex. That's the same thing.
Yeah, I suppose I don't understand how we got the diagram that's written it down. What is it?
This is just this diagram plus this diagram.
But you have in the down diagram F.
Well, not exactly. Right. I'm just drawing the diagram for the retract, right? And then I have this map F prime, and then I'm drawing the lifting diagram for this F prime. So this additional square is the lifting problem for the F prime and some G in the S. Right? Now I'm observing, since these two compositions are the identities, having a lifting like this in this small square is the same as having lifting in this big rectangle.
Oh, I understand. You have a misread. It's F prime F from left to the right. It's a down diagram, I suppose. It's F prime F, F prime G.
Yes.
Okay.
I just was in a hurry. Yes.
Yeah, then it's okay.
So solving this lifting problem is the same as solving for the big rectangle. So now I have a solution for this lifting problem, since I know that F is in the left complement. So the solution of the lifting problem is just the composition of these two maps. Okay. This was just kind of some simple observations. And for transfinite inductions, you indeed need to do some computations. It's not immediately clear that this is the case. So let's do the compositions. So I assume that I have a situation like this. So I have a functor from the ordinal to the category C. And it will be convenient for me to, instead of writing this functor, look at this data. So I have objects x beta, and I also have maps f, say, gamma, beta. So these are maps, and the this we call them gamma. So giving such a functor is the same as giving this objects and the maps. So what we need to show is that if I consider diagram x0, this is mapped to the x. So now I need some notation actually for the objects. So G, which is in the S. So here this is x alpha, and this is the map f alpha 0. So some V, and this is some V. So for this we need to construct a lifting for this diagram, right? Because this map from the x0 to the x alpha, this is exactly the transfinite composition. Okay, we will just construct, we just solve a more general problem from which this follows. So we construct, well, to say, to find sigma, we more generally construct morphisms, so some which I'm going to call u beta. And this will be from the x beta to the x, and this not just will be just one morphism, but this whole series for all beta, this we call then alpha, satisfying two conditions. So the composition of the G u beta is equal to the V f alpha beta, and u beta is u gamma f gamma beta. So for beta, this we call them gamma.
So is there a fixed alpha on x? What is it?
Well, it's just something. Well, maybe it's not a good notation. Maybe you can write z, but this is without index, so you can distinguish them.
And x alpha is equivalent.
Hmm?
X alpha is equivalent.
Yes. And the map from the x0 to the x alpha is exactly transfinite composition. Okay. So, of course, the construction is by transfinite induction. So we consider. We consider that say gamma is less or equal than alpha, and assume that morphisms u beta, where beta is less than gamma, have been constructed. So we want to construct them, this morphism with such properties for the gamma. So we consider three cases. So the first case is kind of trivial, but for completeness, I want to include this. So in the first case, gamma is just 0. So in this case, we can just set that u gamma is just u. Okay, so the second case is this is, we do some work. So gamma is of course non-zero, limit ordinal. So then of course we can say that the x gamma is isomorphic to the colimit of the x beta for all the beta less than gamma. And there is unique map u gamma from the x gamma to the x such that u beta is equal to the u gamma f gamma beta. Maybe to easily understand why we have unique map such this, well, this is just because we have a colimit more or less, right? But we can also draw this using the diagram. So we have u beta to the x. So here we have f gamma beta, x beta, and then there is a unique map making this diagram commutative. So this is why we have a colimit. Okay, so this is automatically give us the second identity, and we need to prove also that there is a first identity, but this also more or less follows immediately from the fact that we have a colimit, right? Because maybe I just squeeze additional computation here. So we have commutative square like this. Right, so this is by assumption, and the commutativity of that square is just this identity, right? So this has to be the same, yes. Now, but so this arrow, this object depends on the beta, and I can take the colimit using beta. Right, so if I take the colimit, I'll produce another commutative square. So here I'll get colimit x beta. The colimit of the u beta is called u gamma x g y, and this is x alpha. This is now f alpha beta, and this is v. Okay, so the commutativity of the second square give us exactly this identity, but for gamma. Wait, this is not beta, this is gamma, sorry. Okay. And this finishes the case when we have, so the second case where we have a limit ordinal. And the last case, number 3, is when gamma is the successor ordinal. So gamma is beta plus 1. So then u gamma is a solution of the following lifting problem. Right, so you consider x beta. This is mapped with the f beta plus 1 beta to the x beta plus 1. So here there is a composition of the v and f alpha beta plus 1 map G, and this map is u beta. So there is a solution, of course. Well, since we assume that the map F with indices beta plus 1 and beta, this was in the S by our assumption, that this is closed under transfinite compositions, and yeah, so in the left complement, and the map G is in the S. So this is u gamma, and this finishes all the cases for transfinite induction. Okay, so you can see this is kind of a little bit technical in the sense that we need transfinite induction to prove this, but it will be important for many computations to understand that this left complement is the weakly saturated class, but this is probably maybe just one place in the course where you need transfinite induction, so you can as well just take this result, apply it to something, and forget about the proof. And if you've seen transfinite induction before, this is probably quite very simple and standard for you. Yeah, I just wanted to give you an exercise on transfinite induction. again, you kind of do this, separating this into the same steps. So exercise, which is important for understanding the theory. So proposition, which will be the exercise. So the class mono, of course, of all monomorphisms in simplicial sets is weakly saturated. So again, you verify this is closed under three operations. Logic is more or less the same. Computations are, of course, a little bit different. So then, you can also use this to get the following result. We can consider the definition. Now I work with simplicial sets. So consider the category of cells, sorry, not the category, so the class of cells. So this is by definition the class of maps, which is the inclusion of the boundary of the standard simplex to this standard simplex. So this is, of course, some, well, in this case, just a set of morphisms in the category of simplicial sets. And then doing this transfinite induction showing that this class of monomorphisms is saturated, you can derive from this corollary, which is another exercise, is that if you take cell, take the weak saturation, you exactly get the monomorphisms. So, and this is a very nice result, right? So you have this huge class of all the monomorphisms, and you can understand this is just a saturation of a very small and understandable class of all cells. So I'm leaving, well, if we can automatically get the inclusion in one direction using the previous proposition, and there's kind of small computation to show that there is inclusion in the other direction, so this will be another exercise. Probably I'll add this to the first assignment. Okay. And maybe, so how much time I have? I'll still have. So maybe I'll immediately fix some classes of morphisms that I'm going to use in this course and fix notation for them. Maybe just in one place. Otherwise I can forget what I already defined and what I have to define later. So in the category of simplicial sets, so let me call this as some classes of morphisms in the category of simplicial sets. Just small subsection about notation. So I'm going to use class horn, and this will be by definition just the inclusions of all the horns. So lambda ni inside delta n for all n which is at least 1, and all I which is between 0 and n, including 0 and n. So then there is the subclass or subset in this case of left horns. So again, this is inclusion of all the horns as before, but now I assume that this index I is not equal to n. So it's between 0 and n, but for n this is strictly smaller than n. I don't include one of the boundaries. And there are also right horns. So right horns and finally there is also the notion of the inner horns. This is just an intersection of the left and right horns, right? So but maybe explicitly I write this as the inclusions of the horns. And now in this case, n is at least 2, and I is between 0 and n. It's not equal to 0, not equal to n. Okay, so these are horns, and with any class of the morphisms, we can associate two other classes. We can take a weak saturation, or we can take a complement. Well, actually, three classes. You can take left complement or right complement. Okay. So, maybe definition. There's several parts. So maps, if you take the class of horns and take the saturations, are called anodyne maps. Right? And then there are parts 2, 3, and 4, and this is for the left anodyne. Right, instead of the closure of the horns, you just take left horns. For the right anodyne, you take the closure of the right horns, and there's also notion of the inner anodyne. So this is, maybe I just write it here. So this is left horn closure, this is right horn closure, and this is inner horn closure. So that's our left anodyne maps. Well, we clearly have a bunch of simple inclusions, right? If you have, and yeah, for the notation, I don't want to introduce notation for the anodyne maps. I'm going to use throughout this course just left, right, inner, or just horns with this bar. So next two inclusions are completely obvious. So clearly anodyne, inner anodyne maps sits inside the left anodyne maps or right anodyne maps. And this is all sits inside the all anodyne maps. And then for the right complements, we have the following notion. So maybe just another definition. Again, these four parts. So first part, what we call the right complement to the horns. We already discussed this. Yes. No. We just by definition, I think it was in the previous lecture, you wasn't here, so this, yeah, this was scan vibrations. So, and just for shortness of the notation, this is called the just vibrations. So vibrations, this is the right complement to the horn. And then we have all other kind of vibrations, left, right, and inner. And I'm going to use notation something like this. L, left vibrations, this is left horn, right complement, 3 right vibrations, this is right horn, right complement, and then for inner vibrations, this is inner horn, right complement. Okay. So this is just by definition. And also, I can introduce one more notion. So this is another definition. The trivial vibrations. So the class of trivial vibrations. I'm going to write 3 fib for this, for trivial vibrations. This is by definition. You take the cells and you take the right the complement to the cells. Okay, so then analogous to this inclusions of the anodyne maps, I have inclusions for the vibrations. So for example, I can say that the trivial vibrations are contained in the vibrations. Okay, can you tell me why trio vibrations are definitely contained in the O vibrations?
Потому что если мы можем продолжать работать, границы это же типа опа еще
Я не уверен, что я понимаю, как это работает, такое объяснение. Well, actually, the simple observation, well, since this both defined as the right complements, right, vibrations and trio vibrations are defined as the right complements, to prove that you have inclusion in this direction, well, you can notice that when you consider horns, then these are, every horn is a monomorphism, so this is in the weak saturation of the cell. Hence, any trio vibration is a vibration. That's a kind of very simple observation, but if you know model categories, well, probably you used to define trio vibrations as the weak homotopy equivalence as positive vibration, two properties together. This will be equivalent, so this kind of explicit definition as the right complement to the cell, this will be the same thing as the vibration plus weak homotopy equivalence, but we will return to this a little bit later when we have more theory. So this is kind of non-trivial inclusion, which requires some argument. But other inclusions, for example, if you take vibrations and include them in the left vibrations or the right vibrations, this is simply by definition, right, as the right complements plus inclusions of the horns that you have. And of course, left to right vibrations sit inside inner vibrations. Okay, so these are the classes used in this theory. Not all of them, but a large portion of the classes of the morphisms that we will need in these lectures. And later, when I return to these things, I'll probably redefine what I mean by anodyne, some sort of vibration, just to give you the examples what we will see in this course as the classes of morphisms. Okay, so next, I want to introduce some notation and some basic properties of the related notions. So given maps, so you can think about this in simplicial sets, and we'll use this in simplicial sets, or you can think about this as in any category. Actually, I think it works. So given maps F from A to B, G is a map from K to L, and H from X to Y. Yeah, probably we need something like Cartesian closed. Let me assume that this is in a Cartesian closed category. So then we can define first push-out product, which is simply really not a new definition, but just notation. So push-out product of the F and G. Notation for this is just a box. And this is the canonical map from the product of the A and L over the product of the A and K with B and K. To the product of the B and L. So in other words, I have the following push-out diagram. So I have A product with K. So this is mapped inside A product with L, and B product with K. So then take a push-out, right, which will be this thing. Right, and then product of the B and L has clearly maps from here and maps from here. So this is just induced by the map F from A to B, product with the identity on L. This is just a map identity on B and map from K to L, which is G. And then there is a unique map here, which you'll just want to use short annotation, F product with G. So push out product with G. And there is a dual notation for the homes. So F, G, and H as before. So then I can consider, say, home. Well, since this is an internal home, I want to write home. So from L to Y, this is mapped to the home from K to Y. Then there is also home from the K to X. Right, again, this is just induced. For example, if you look at this map, this is induced in the second argument from the map from the X to Y, so induced by the map H. So this is in the first argument is contravariant, so this is induced by the map G. So we have these two maps. You can form pullback. So this will be a lot of symbols. So let me squeeze this home L and Y. This is taken over the internal home, taken over the internal home of the K and Y, and here's the home K and X. So then we'll take internal home between L and X. Again, there are induced, G induces map here, and H induces map here. The square is commutative, so there is a unique map like this. And notation is for the H to the square G. So this is part 2 of the definition, pullback home.
Why are our categories a big position?
Well, because actually in the main application that I have in mind is for the simplicial sets. And for the simplicial sets, I want this map to be not just a map between homes and this pullback of homes, but for the internal homes. I don't see, well, I think you can definitely generalize this to the case of other categories which are not necessarily Cartesianly closed. Maybe instead of the internal homes, you just get ordinary homes. Well, sure, we can do this. But this is what I need from the point of view of applications. Okay, so that's a notation. So remark. Simple remark. So clearly, it follows from the definition that if you take the push-out product of F and G, then this is isomorphic to the push-out product of the two maps in the other order. So this is symmetric. But of course, pullback home is not symmetric. So very simple remark. Okay, so proposition. So I want to give a name for this proposition. I'm going to call this a junction of the lifting problems. And this is why this notation is, I like this notation so much, because you can formulate problems or formulate statements in a very short way. So for example, this proposition, which is the adjunction of the lifting problems, is just the following. For example, you can take the push-out product of the F and G, right, and consider the lifting problem with respect to the map H, and has solution if and only if map F has a solution with the lifting problem with the H pullback home G. So these two lifting problems are just equivalent, right? And if you don't introduce this notation, so I'm going to write explicitly what it means. If you don't introduce this notation with the push-out product and pullback home, you're forced to all the time say, well, here this is just an example, something like this, that so i.e. The following two lifting problems are equivalent. So the first one is where you have A product with L, co-product with B product with K over A product with K. So this is mapped to the X is mapped to the Y, this is B product with L. So this is some U and V. This is maybe some map H, this is W, and this is push-out product of the F and G. So there is a lifting problem like this, where left-hand side has a very specific form. So this is equivalent to the following problem. So home Okay. So to get these diagrams, of course, I just plug in the notion of the pullback home in push-out product. So if you don't have this notation, you need to say something like this, that you look at this lifting problem and that lifting problem, that if you have solution of this happens if and only if you have solution to this lifting problem. So as you can see with this notation, it is much easier to formulate, and when you actually do the computation with a lot of these vibrations in anodyne maps, horns, etc., when you have something like this, just as a formal step in the proof will be, I don't know, 10 times shorter than you write all such diagrams all the time. So it might be look a little bit confusing when you see this for the first time, since there is kind of a lot of information, diagrams is not very nice. But when you get used to this, you appreciate how useful this notation is. For example, I'm pretty sure if you take Keradon and use this notation where you can use it, it will be something like maybe 10 or 15% shorter, instead of writing these diagrams all the time. Okay, what about proof of this thing? So how much time I have?
So you have equivalent notation for the child product and pullback home, yeah?
Hmm?
You have the same notation for child product and
No, no, no.
pullback home.
No, notation is different. So this is kind of everything in one line. And this is so if you write this in tech, you write something like this. Right, so this is supposed to be something like a power. So notation is different, otherwise you cannot distinguish them, and that's a problem.
Yeah.
Sorry, but we can't see the difference.
Не, ну типа видно.
No, I think you can see the difference here, between here and here.
Now I think I can. You can see understand the difference. Before the explanation.
Oh, clearly, if you look at the definition, and for example, this remark, you see this is different motions, since this is clearly symmetric, this is not symmetric. So they can be the same.
Yeah, and this everything going in some manual category or what?
So in my case, well, actually, I need this for only for the category of simplicial sets. So if you think that this all that's just simplicial sets, that's fine. But since I use the structure of the product here, I call this as Cartesian closed. But if you replace this with some other monoidal category, I think this still works. There are no problems. Yeah, and for the second part, it has to be closed. Otherwise, you cannot formulate this. Yeah, the proof is kind of more or less a straightforward exercise in just understanding what's written. For example, you take one of the diagrams. For example, we take the first one, and you try to understand what the data you have here, right? So on the first diagram, you have map U, which is the map from the product of A and L to the X. You have map V, which is a map from the B product with K to the X. And you have map W, right? Just to form this diagram, B product with L to the Y, right? So yeah, and also something else, yeah, and there's also this map S. I'm going to call the lift S, and so S is a map from the product of the B and L to the X. Okay, so and there are kind of some conditions. So there are maps of this kind, as I wrote, 4 maps, and there are some conditions that, for example, these 2 triangles are commutative. So then, by adjunction, right, in this case, just the adjunction between the Cartesian product and the internal home, I will produce a maps, for example, or I will get U with the tilde. This is from the A to the internal home of the L and X, right? So you have a map like this. By the adjunction between the Cartesian product and the internal home, you get a map like this. And everywhere you have a map from the product, so by adjunction you get all these other maps. So V with a tilde, W with a tilde, and also S with a tilde. So S is with a tilde is this lifting. So everything on the second diagram, everything is with a tilde. So this is from the B to the internal home of the L and X. Yes. Right. So by the adjunctions, you get all the maps here, and once you realized how data on one diagram is related to the data on the other diagram, and the adjunction preserves everything, I leave it as an exercise to check that the commutativity of these 2 triangles is the same as commutativity of these 2 triangles for these maps with the tilde. So this is a very simple proof. You just have a lot of data that you can kind of manipulate at once. Okay. So we have this. Yeah, and whenever we have this kind of general result of this sort, yeah, it is convenient to look at the special cases, because in special cases you can also, when you have adjunctions of this kind, adjunctions of the lifting problems of this kind, you can also get something interesting. So, like in this remark. So first remark. So consider special case. So in the special case, you can take A to be empty, or A to be empty, or Y to be just a point. Well, empty, of course, means initial object, and point means the terminal object. So in this special cases, you still get something interesting. Like, for example, if you take, so give non-trivial equivalences of lifting problems, for example, let's look at the case when K is empty, and I also assume that Y is just a point, right? In this case, I'll get the following, that I have a lifting problem for the map which is a product of F and identity on the L. So I'm asking for the lifting for the just the map X to the terminal object, right? And this lifting problem is equivalent to another lifting problem where I have A is mapped to the B using map F, and this lifts using the map from the internal home Lx to the point. So this, for example, equivalence of these 2 lifting problems is just a special case of that general statement, as you can easily verify what happens with those diagrams if you plug in empty and the point. And in other examples, I'm going to prove some kind of adjunctions of lifting problems. You can automatically, kind of, as an exercise, always check what happens in these special cases. Okay, second remark is it's not something that we immediately need, but just kind of nice categorical restatement of what we've done in this proposition. So you can consider category, so maybe I call this arrows of C. This is just the functors. Oh, actually, I think I call this already morphisms. So more C, functors from the one underlying to the C, so just arrows. So this is closed symmetric monoidal so with the push out product as the product, so this is monoidal product. And the internal home in this case, so home underlined, so I'm claiming this is closed, so between say B and G, this is B to the square G. So in other words, we have an adjunction like this. So if I consider the category of the morphisms in C, then A product with G, push out product with G, comma B, is naturally isomorphic to the home in the category of the morphism C from A to the B pullback home G. So if you're not satisfied with this kind of as a formal notation, you have a categorical interpretation. So you start with some Cartesian, closed Cartesian category, and then on the category of the morphisms in this category, you get a symmetric monoidal product, which is also closed. Okay, and I'm just giving you one simple remark, and then I finish the lecture, which is, if you look at this kind of explanation why this works, all we actually used is just the adjunction. So you can formulate as follows. So you can take A to be some morphisms in some category C, take B to be some class of morphisms in some category D. And suppose you have an adjunction, so F from C to the D, and the functor in another direction. Well, I call this U for the free and forgetful functors, the standard situation. So then, by more or less the same argument, but in more abstract way, you can prove the following adjunction between lifting problems. So the same proof works in more general situation. Okay, so with this simple remark, I finish the lecture. Yeah, this is just the adjoint functors.
I also want to ask, so you make morphism C into a category, how do you do it?
Well, this is just one underlined, right? Right. This is just a category with two objects and one arrow between these two objects. So this is just a tautological definition, right? If you look here, what lives here? This is just two objects and the map between them. That's an arrow or morphism.
Okay, and so what is a morphism in morphisms?
Commutative squares, right? You have two maps, right? And the map between them is this commutative square, which also follows from this formal definition, because this will be natural transformations of functors, and that's exactly commutative squares. Okay.